On to lesson number 2, and we're talking about linear regression.
All right.
So linear correlation gave us a number
that we could use to measure the strength
yes.
of the relationship between two different variables. Now, linear regression is actually going to, the word regression may help you think of it, is going to work backwards. It's going to take the data points and work backwards to try and give you an equation. What you've been doing in math for years, you've been taking an equation and then turning that into points on a graph. So this linear regression, we're going to take this scatter plot and we're going to try and create an equation of a line of best fit that we can now use to help us make our predictions. Okay, so this is going to be, using that relationship to create the line, the y equals mx plus b. That's what we're going to do.
So onwards, we have this thing called a least squares method to find the line of best fit. Drawing a line of best fit usually involves some compromise, right? We have to move the line closer to some points while increasing its distance from other points. Some points, are above the line. Some points are below the. Whatever we do, we get a compromise.
Yep.
Okay, so the least squares method takes that eyeball approach of drawing a line of best fit, formalizes it, and gives us a very precise method for determining the absolutely best possible line of best fit.
And this takes away that thing that would happen to you in grade 10 science class where you draw your line of best fit using what you think are the best parameters, then you look at your neighbor and their line is different.
Yeah.
Right? And so this is going to take that away completely. So there's no opinion, this is high, this is low, this is here, this is there. We're going to actually do this mathematically.
All right. So residuals. A residual then is the vertical deviation from each data point to the line of best fit.
Right.
So we know what deviations are. It's how far away something is from a standard value.
Yep.
So this is the vertical deviation that each data point is from the line of best fit.
That's right.
Okay. Residuals then are positive for any points that are above the line of best fit.
And this is just like your deviations are positive for any points above your mean.
Yeah.
The residuals are positive for points that lie above your estimated line of best fit. Residuals are negative for any points that we think lie below the line of best fit.
line of best fit.
Okay, so that's it. You positive and negative residuals.
And so we at this point we don't even need to worry about calculating residuals or what they are. We just have to know that a residual is basically a deviation
vertically,
and that deviation is positive above the line of best fit, and it's negative below the line of best fit.
Let's visualize this. So in your note, you've got a little set of axes, and here's what we'd like you to draw in. So in your set of axes, label X and Y, draw in a line with positive slope here, and
some data points.
Sketch in some data points, okay?
Okay.
So what this means is that if this is the line of best fit that Excel says would be suitable, then this point would have a positive residual. Okay, and this point would have a negative residual. Okay, so it's just the deviation, the y value deviation. And so you've got points lying above the line, points lying below the line, and those are your vertical.
Yeah, so that's basically a visual representation of what residuals are.
Yeah.
All right, so what's the least squares method? Basically, in the least squares method, this is like background information.
Yeah.
This is what Excel or what we by hand, this is what we're going to do.
Yeah.
We're going to give you the equation to figure out how to do it. But, okay, it's not enough just to plug things into an equation. We kind of need to know why we're plugging things into an equation. So what we're going to do to generate our line of best fit, we're going to say the sum of all the residuals has got to be 0.
Yep.
So
they have
all
to
those
balance
positives
out.
And negatives are going to balance out. And kind of what that's like saying is that we're going to get that perfect line that has the right number of dots above and the right number of dots below, but we're going to do it mathematically. So that's the first thing. The sum of all the residuals is going to be 0.
And I'm going to interrupt for a second just to say that you need the second part that we're about to show you, because I could create a line that actually goes in the complete opposite direction, completely perpendicular to my data cloud, and still get this sum of residuals being 0. Okay, you can draw a crazy wrong bad line and still get the sum of the residuals to be 0. So it actually has to meet the second criterion as well.
So there's a second criteria, which says that the sum of the squares of the residuals has the least possible value. So we're going to, that's why it's called the least squares method. So we're going to minimize the sum of the squares of the residuals.
And so imagine if you were to take that line of best fit and overlay it on top of the points correctly, then not only would the positives and negatives balance out, but because their distances would be small, then their squares or their areas, if you were to take the positive residual squared and the negative residual squared and add them all up, if you were to sum all of the squares
then
of the
it
residuals,
would,
it would be the smallest
the
value.
smallest value.
If you drew the way wrong bad line that is actually running perpendicular, then all those distances, though they balance out to 0, would be so big that their squares would be enormous, and then you'd end up with a much larger value for the sum of your squares.
Yes.
So least squares method, it meets these 2 criteria. This might be a good kind of question for like a concept idea on a multiple choice test.
Yes.
Okay?
Yeah.
You won't have to do anything with this other than apply the formula, but to understand why this works would be key.
Okay, so here it is. Y equals mx plus b. We know that we're graphing straight lines. So that we know that when we're graphing straight lines, we're going to have an equation y equals mx plus b. We need to solve for m, and we need to solve for b. And here's our 2 formulas. M is equal to this guy.
Which is no worse than what we looked at
for
R.
It isn't. And hopefully you trust us now that you said, oh yeah, okay. Basically, we're going to create some kind of a chart.
And we are.
And B is, of course, y bar, which is the mean of the y values, minus m times x bar, which is the mean of the x values. And that's going to give you your y-intercept,
essentially. Okay.
So here we go. When we have the equation of the regression line, we can estimate values and make predictions, right? Because that's another big part of what we want to do. We want to make predictions. Interpolating. That basically means we're going to take basically predictions between existing data points. So within the set of data, and we're going to try and make predictions based on data in between our data points.
In between the points that we actually have gathered, right? You extrapolate. If you take the line or curve of best fit and you extend it out beyond the cloud of the data points, and then you use those values. So as soon as you step outside the range of your existing data points and try to make predictions that go way beyond, then you're extrapolating, okay, extra being out, and then inter being within. So interpolating, you're staying within your data cloud on the line, and extrapolating, you're getting out of your data cloud on the line.
Exactly.
Okay, this is where it gets a little bit less reliable and a little bit more shaky.
Yeah, extrapolating is always a little bit less reliable than interpolating, but we're going to use both. All right. So here is example number 2. A university would like to construct a mathematical model to predict first-year marks for incoming students based on their grade 12 marks. So they want to apply this model then and interpolate and extrapolate, et cetera, et cetera. So here is a very small sample, okay, of students. And we have their grade 12 marks, and we have their first-year average, right? Because grade 12 marks generally precede your first-year average, we say that the grade 12 marks are the
X values.
Independent variable, and the first-year average would be the dependent variable.
Yeah.
Now, you'll notice this chart is much smaller. We have an xy, and we have an x squared. And so, again, we're going to go down this list, and we're going to say, okay, well, what's the sum of x? If I add up all these grade 12 marks, I get 844. Let's do the same. In my calculator, sum up all the y's, I get 761. All right, so piece by piece by piece, x times y, the first value and the second value. And basically, we're not going to fill in the chart. You can do this for yourself, but you would have seen this example very similar. If I take this x value and I multiply by this y value, then I get this number. If I take 90 and I multiply by 83, I get this. And so on and so forth all the way down the list. I add these up, I get this bad boy right here. And of course, then when I do my x squared, I say 85 times 85. I say 90 times 90, 76 times 76. All the way down, I sum this up, I get this. Okay? So, of course, what we're trying to do is we're trying to use these values to manually calculate the equation of the line of best fit.
So we need M. We need B. We need Y bar. And we need X bar. That's what we need.
So here we go. Use the given formulas. We want to manually calculate this. All right, so here we go. Just like we did before, we can bring in you know, we can bring in the data from the columns that we've just constructed.
Yeah.
First, let's do our averages. Y bar is the sum of y divided by n. Okay?
Yep.
So 761 was the total. There's 10 students, 76.1. X bar is the sum of x divided by n, which is 844 divided by 10, which is 84.4. And then m, which is the slope. Okay, so here we go. We got n, which is 10,
yep,
times the sum of x times y. Right? So the sum of x times y was 64,654. Subtract the sum of x times the sum of y.
yep.
That's the numerator.
Notice this is the exact same numerator as for your R value.
Exactly.
So on a test situation, when you have to find the correlation coefficient,
Mm-hmm.
you've found that numerator already, you can just translate it down into this
Yep.
formula. And then, you know, parts of the denominator are also in your formula for correlation coefficient. But that'll just save you a step. All right.
So here's the denominator. N times the sum of x squared. And from that, we subtract the sum of x all squared. And we get an m value of 1.168, which is, of course, slope.
Positive slope. Okay.
Okay?
Yep.
So now let's use B. Y bar we just calculated was 76.1. From that, we subtract the product of m and x bar. We've got 1.168 times 84.4. We put that together. We get a B value, a y-intercept of negative 22.479.
Mm-hmm.
And we put these two concepts together, and here's the equation of our line. Y is equal to 1.17x minus 22.5.
Right. And so notice here that this y-intercept having a negative value. Okay, you wouldn't
Mhm.
have a negative university value
Mhm.
for your first year marks.
Mhm.
And so in terms of extrapolating leftwards, like beyond the data, we probably couldn't take it very far because you wouldn't have a value of negative 22.5 in first year university.
No.
Not if you had 0 for your grade 12 average. You wouldn't even be in university.
Yeah.
So, you know, when you look at this equation of line of best fit, there will be some parameters that would be reasonable and unreasonable. But this would be the line of your best fit. You found y bar, you found x bar, you found m, substitute it in, and now you have y equals mx plus b, which is your negative 22.5.
So now the rest of this lesson, we're going to leave you to try on your own. Because if you get stumped, take a look at the steps from lesson 7.1b, which is basically the steps in Excel for how to create a scatter plot and then pulling out the equation.
Yep.
Okay?
Yep.
Check that equation that you get from Excel with the one you just created by hand. And what you will find is that they will be substantially identical.
Yep.
They will be almost exactly the same.
Only differences would be accountable to rounding.
Yeah, and so if you want to see basically a couple of steps, these are very, very similar. Transfer the table of x and y values, graph an xy scatter plot, right-click and add a trend line, choose a linear regression, make sure that you display the equation and the r-squared value, and then use the equation for part C to substitute, hey, what do we think the prediction is going to be? 82% average in grade 12. What's their first year mark going to be?
All right.
And you'll see that basically you get 73%. So try this. These are the answers. These are a couple of steps to do. Try this on your own, and we'll do lots more questions in class.